Bom dia, pessoal.
Bom dia.
Quem eu não tive a oportunidade de conhecer, eu sou o professor Rômulo, do Departamento de Esporte. À minha direita, a professora Patrícia, do Departamento de Biodinâmica. Eu vou dar aquelas instruções mais administrativas no início. Em seguida, eu vou passar a palavra para a professora Patrícia Brum, para que ela possa apresentar a palestrante da nossa manhã. Tá bom? Então, a velha e boa lista da pasta amarela, que é para aqueles que estão regularmente matriculados na disciplina da pós-graduação. Aqui dentro está, não está mais dentro, agora está fora, vou deixar assim. Essa lista é para quem deseja receber o certificado da palestra dessa manhã, tá bom? Quem optar por preencher essa lista, faça de forma legível, por gentileza, porque os dados que serão gerados para o certificado serão tirados daqui, ok? Hoje é o nosso último encontro, né, para quem está na disciplina da pós, e vocês ainda precisam fazer a resenha da apresentação de hoje. Como a gente não vai se encontrar, pelo menos formalmente, daqui a 15 dias, eu vou pedir para vocês deixarem a resenha da apresentação de hoje no meu escaninho do departamento de esporte. Não sei se vocês conhecem aqui, mas atrás da gente está a diretoria, tem um bloco administrativo que tem a diretoria e a secretaria dos departamentos. Lá tem a secretaria do departamento de esporte, é super fácil achar. Eu tenho um escaninho que vocês podem deixar as resenhas lá, até sexta-feira que vem, para que a gente tenha hábil de ir lá, retirar, corrigir nessa nota de vocês. Tudo bem? Tranquilo? Então, eu vou pedir para a professora Patrícia Brum, por gentileza, fazer a introdução do professor Scott. Obrigado, Patrícia.
I will introduce Professor Scott. Scott, if you excuse me, I will just talk a little bit in Portuguese and then I switch to English, okay? Pessoal, é uma honra apresentar aqui o professor Scott. Deixa eu botar o óculos, senão vai falhar aqui. Eu conheci o professor Scott na Noruega, quando ele era postdoc na Alemanha. Vocês vão ver o trabalho interessante que ele faz. Ele trabalha com caquexia, perda de massa muscular nas doenças. E ele vai mostrar o trabalho dele com pacientes e com animais que ele conduz, tá? E ele é inglês, né? É formado na Universidade de Leeds. Depois ele conseguiu uma bolsa bem prestigiada na Europa, que é Humboldt, para estudar e fazer seu postdoc na Universidade de Leeds, com o professor Volker Adams, que é um fisiologista muito reconhecido, né, na nossa área, trabalha bastante com exercício e doenças crônicas, né, e ele tem bastante interesse no estudo de mecanismos da perda de massa muscular, e ele trabalha com mediadores moleculares, ele trabalha com músculos respiratórios também. Ele me falou que vai fazer uma exposição mais breve, uma meia hora, 40 minutos, e vai abrir para que vocês façam perguntas. E daí eu vou passar o microfone para vocês ficarem bem à vontade. E qualquer coisa a gente ajuda, tá bom? O importante é a gente aproveitar. Pedir para ele falar devagar também, tá bom? So Scott, thank you very much for visiting us. It's a pleasure. I was telling them that the first time I met you, it was in Norway. Do you remember? And when he was a postdoc at Leipzig University, and he's a brilliant researcher, studying a really interesting topic in exercise and chronic disease. So I will invite them, Scott, to come here and talk. So the floor is yours. Thank you very much for coming.
Obrigado. Do I need to use the microphone?
It's good because of the recording.
Okay.
Thank you.
So I'll go to the other side of the room because I can see everyone.
And I will,
Okay, so thank you very much, particularly to Professor Brum for the invitation. It's my first time in Brazil, And so far it's been brilliant. This is your winter, it's amazing. It's better than the summer in the UK. So today, hopefully we'll have a bit of fun. You know, it's supposed to be a good chance for me to get across some of my research, and more importantly, for some of you to learn something new. Well, it's going to be on. Here we go. So those of you who really like your blues guitar music, bless you, you will get the title, My Broken Heart Gone Done Me Wrong. And what we're really going to focus on today is when we get a damaged heart from chronic disease or whatnot, how actually that can really have some severe consequences, not just for the heart per se, but also for the rest of the body. And what we're really going to focus on is the skeletal muscles, particularly the legs and the diaphragm, the main breathing muscle. And hopefully some of these strange abbreviation, ring fingers, ROS, and melting thighs, that will become a bit more clear as we progress. Okay? So let's get underway. So let's start here. We all know who this guy is, Steve Jobs. Absolute genius. Sadly, he passed away. David Bowie. I think all of you appreciate his music. Bit of Ziggy Stardust. So you're probably thinking, okay, I've come to see a scientific talk, so why are these two celebrities on the slide? Well, what we can clearly see is this is Steve Jobs in 2005, and if we fast forward to 2011, we can see a lot of weight has been lost. He looks quite ill and gaunt. And again, David Bowie, we can also see the same. This is when he was living the high life, but sadly he succumbed also to this gaunt, cachexic look. And both of these died sadly from cancer. And typical with many diseases, cancer, heart disease, lung disease, people lose weight, lose a lot of muscle mass, they become very disabled, and they can't continue their normal daily activities. So what we're gonna, bless you. So what we're going to talk about today is really finding out, well, why does this occur? Okay. If we look at reduced muscle mass, we can see this very gaunt image, and this is an MRI or CT scan typically done. We can see this is a young person looking at the leg muscle, the thigh muscle, and we can see with age we lose a lot of this muscle bulk and replace it with fat, okay? And that definitely contributes to reducing the amount of exercise older people can do, and also just typical everyday activities. You know, just playing with their grandkids, even hoovering the house, etc. And often, when we go a bit more scientific, we actually can take a biopsy, and we can really start to look at the size of the muscle fibers. And this actually is a typical example in the diaphragm. So this is following mechanical ventilation. And these are healthy fibers. These are staying for slow and fast twitch fibers. But what you can really see is actually this is just after, I think, around 24 to 48 hours, we see a 50% reduction in fiber size. Okay? So when we do lose muscle mass, this can actually happen within hours. Very rapid, reducing quality of life. Muscle wasting, so it's also termed fiber atrophy. So it's a loss of muscle mass, and it's mostly consequence to reduce muscle fiber size. And what's important to note here is actually body weight may not change. Okay? So many people actually lose muscle mass, but their body weight doesn't change, or it may even increase. So it's not so easy to actually see this appearance. Cachexia, when we looked at Jobs and Bowie, what we can see is that really gaunt loss of body weight. Okay, that's much more apparent. And that's defined as greater than 5% over 1 year loss of body weight. And it may or may not include the loss of muscle mass. And finally, sarcopenia. So this is the loss of muscle mass, particularly associated with aging, okay? Sadly, it's going to come to us all aging, so hopefully we can actually slow this rate of muscle mass loss. That's really important, and we know now with the increase in aging population, this is going to become, and it already is, a tremendous problem, okay? So if we can keep older people healthier and more independent, that's going to really help socio-economic status in many countries. Okay, so if we look at muscle wasting in various clinical conditions, just to show this is a pretty big problem. Well, as I mentioned, many chronic diseases such as cancer, heart failure, acute illnesses as well, so mechanical ventilation, critical care illness, sepsis. We mentioned sarcopenia, that's age-associated loss of muscle mass. Disuse, this probably affects more of you in the room because you're quite young, okay? So you may play sport a bit too aggressive one day and you break your leg. That's not very nice, but you lose some muscle weight, but luckily you can recover. Great, okay? You're still young enough, and it gets a bit more tricky as you get older. Space flight, I don't know if there's too many astronauts in the room, I don't think so I'll skip that one. And also, we can look at nutrition and dietary. If we starve ourselves, we lose muscle mass. And also certain drugs that are given to treat certain diseases, in particular inflammatory conditions. Many of your grandparents may get glucocorticoids, and they actually are great for reducing some inflammation, but they actually increase muscle loss. Okay, so there's that actually double balance, which makes things very difficult. So why should we really care? Hopefully, I think you're already at the point where you already care a bit about muscle mass loss, why it's important. Well, skeletal muscle is the largest organ in the body by mass, okay, typically 40%. It's very important for locomotion and breathing, okay? And also, often it's underappreciated, but it's a very important organ for metabolic regulation. Think about type 2, or think about diabetes and glucose regulation, where most of the glucose is taken up into the skeletal muscle. And this is a really nice data set and figure of what we can see. So these are some ovarian cancer patients, okay, and they followed them over up to around 12 years, and what they could see in the patients that either had a loss of skeletal mass or a gain of skeletal muscle mass, okay? And we can start to see this separation. Those that continued to lose muscle mass actually were all dead within pretty much 5 years. But those that actually managed to maintain or even start to gain muscle mass, we can see their survival was around 50%. And this is 10 years later. So it seems to be a really key driver, not just for quality of life, but for survival. So the lab, my lab, what we really focus on are, well, what mechanisms cause skeletal muscle weakness, and this includes muscle wasting and also just loss of muscle strength. We'll go into a bit more detail of those two mechanisms. And what therapeutic interventions can we actually use? At the minute, there's no treatments for muscle wasting and muscle weakness. So we need to develop something, and we need to develop something pretty fast because it is an urgent issue. So what we really want is some treatments to get this guy looking a bit more like him. Okay, maybe it's a bit unrealistic, but you know, maybe I've had a bit too much sunshine the last few days. But we want to get it somewhere like this maybe, okay? That's the idea anyway. So, at least in my lab, and you'll see some data today, what we typically do, we have a translational approach, okay? So, we use some animal models and try as much as possible to translate that up to human patients. We have numerous interventions. A lot of it is focused on exercise training, so I think a lot of you in here will be interested particularly in the exercise training, the mechanisms why we improve with exercise training. And also drug treatments, okay? And exercise is great because it helps us to actually identify certain mechanisms. And once we know those mechanisms are causal, we can then develop drugs to mimic exercise training. You know, I think it's important to realize most of you here may always say exercise, exercise. That's great, but we're young, so, well, you're young, and it's easy to do it at the minute. But once we get older, once we get ill, frail, it's actually really, really difficult to perform exercise. So for those bedridden patients, we really need to get some drug treatments to at least get them out of the bed, stop the wasting, and then they can actually start doing some exercise. So we use some functional analyses as well. So in vivo, in vitro, muscle fiber stuff, important to look at the functional importance. And then, looking more at the molecular mechanisms, the biochemical causes of what's really underpinning the wasting, the muscle weakness. So the lab is in Leeds. So you can see Leeds is not the biggest city. There's around 500,000 people. It has an airport. That's a big advantage. Just above Manchester, a few hours from London. There's around 30,000 students at Leeds University, so it's one of the biggest universities in the UK. Great football team, 40 years ago. Okay, so I know you Brazilians, the way you play football is, it's amazing, fluid, attractive. If you want to see how real football is played, then go and watch the Leeds United team from 1970s. Proper two-footed tackles, karate kicks all over the place. Go and watch some of that on YouTube, you'll enjoy it. We also have really good beer up in Leeds, so it's a bit darker than your typical beers here. I've been tasting a few of those in the last few days. That's been quite a treat, particularly in the heat. These light beers are good, but typically we drink proper ales and they're a bit darker and heavier. Okay? And of course you need an umbrella, because 350 days of the year you probably get some rain in Leeds. But it keeps the grass green, and that's great because there's lots of sheep, so everyone's happy. Okay, so let's get going into some data from the lab. So let's start with introducing Madame Dropsy. Okay, so you can see Madame Dropsy, she looks quite an important person, but she doesn't look too healthy, does she? She's quite overweight, and in particular, dropsy, that's actually the old-fashioned term for edema or fluid retention, a typical characteristic of heart failure patients when the heart doesn't function correctly. And this is from 1817, and we think it's the first photograph of actually a heart failure patient, or at least when they correctly diagnosed it. And if we currently look at the prevalence of heart failure, we're looking at 2% of the population will develop heart failure. Typically, in the 60s it is general, but a lot of 40 and 50-year-olds also develop it. Post-diagnosis, we can see mortality rates very high. So 5 years post-diagnosis, up to 50% of patients will be dead. Okay? So we really need to try and reduce that and start treating these patients with better options. And if we look at the prevalence, that's still increasing. Okay, it's one of few diseases that actually is still increasing in prevalence. So this is actually already a major problem, and we have very few treatments for this. At least in Europe, we're looking at 15 million Europeans currently diagnosed. So, the main symptom of heart failure is exercise intolerance, and if we go back many, many years ago, so even the great Hippocrates in the Greek times noticed that these type of patients, flesh is consumed and becomes water, the shoulders, clavicles, chest and thighs melt away, okay? And what Hippocrates was obviously talking about was muscle wasting in heart failure, okay? So now you see the melting thighs at the start. A lot of it can be traced back to the Greek times, Hippocrates. So as I mentioned, many clinical conditions are characterized by muscle wasting and weakness. It's an independent predictor of quality of life, okay, as well as mortality. The prevalence of wasting, particularly in heart failure, you're getting up towards 50% of patients. Okay, so that's quite a large proportion. If we look at some some more hardcore data, what we can see here is, in particular, so these heart failure patients, they were tracked looking at the levels of muscle wasting and also mortality. And if we look at 12 months post-tracking, we can see that we had around a 30% survival, okay? In those that suffered both muscle wasting and exercise intolerance, okay? If we look at wasting alone, well, we're looking at 40% of patients have died within that year. And that seems to be even more strongly predicted than exercise intolerance. But typically, the main symptom, exercise intolerance, linked with muscle wasting, a key driver of mortality. Okay, so those of you who haven't gone to sleep quite yet would have noticed that's me many years ago when I still had a bit more hair and not so many lines on my face. That's when I was actually doing my PhD, and we did some cardiopulmonary exercise testing with heart failure patients. So many of you may currently do some of the CPEX testing, CPET, cardiopulmonary exercise testing, and what we can do to measure the level of exercise intolerance is sample oxygen uptake, pulmonary oxygen uptake, and they perform cyclogometer exercise to the peak, okay, so the maximal effort, and this is termed VO2 peak, okay? And that really gives us a good level of how severe their heart failure is and levels of limitation. So what we did a few years ago, and this is an ongoing clinical study, we actually got patients to perform an additional sprint phase. So we give them 5 minutes recovery, then the heart failure patients, they once again go up to the similar work rate, what they got to here. And interestingly, we didn't think we'd see many effects, but we've rolled this out now in the clinic in Leeds, and in over 200 patients, we're actually seeing around 50% of patients can actually significantly increase their VO2 peak, okay? So that actually has pretty important prognostic information for these patients. And what we think a lot of this is related to is they're priming the skeletal muscles, okay? So rather than cardiac function, we think a lot of it's related to peripheral improvements. In the talk today, we're going to focus a lot more on the periphery. You know, a lot of you, particularly whenever I speak to clinicians, cardiologists, they always say to me, you know, why are you even looking at the periphery and the skeletal muscles? You know, they've got heart failure, you should be treating the heart. But we've said their main symptom is exercise intolerance, okay? Typically assessed VO2 peak. And what we can see when we plot left ventricular ejection fraction, so a typical measure of cardiac function, that really poorly correlates to levels of exercise intolerance. So what does this suggest? Well, it must be, well, the periphery must be playing a key role in many of the symptoms that heart failure patients suffer, okay? So next time you see a clinician and they keep going on about heart failure, we need to treat the heart, think about these data, okay? And heart failure is much more of a whole body disease, okay? So what are some of these peripheral limitations? Well, of course we have some impairments in the heart, it's heart failure, but we could also have pulmonary effects, okay? Pulmonary congestion in particular limits breathing. Endothelial effects, decrease in nitric oxide bioavailability, for example. But today we're going to particularly focus on the limb muscle and the respiratory muscle, so both skeletal muscle, but often the diaphragm is ignored or forgotten. But think about heart failure patients, one of their main symptoms is breathlessness. And some of that is actually driven by weakness of the diaphragm, the main inspiratory muscle. So hopefully by the end of the talk you may think the diaphragm is actually the king of all the skeletal muscles in the body. Now, you're all using the diaphragm at the minute, but you don't really think about it. So these are some data from our clinic, and what we can see is if we look at the respiratory, so the diaphragm muscle, and take a measure of its function, we can see using maximal inspiratory pressures, we see around, a 30-40% reduction. Let's say diaphragm function. When we look at the limbs, we see, not such great effects, around 20% or something. And it's interesting when we plot these data, it seems to be the diaphragm is actually in a lot worse state than what we think the limb muscles are in terms of function. So what really causes this muscle weakness in heart failure? Well, this is very simplistic. So, sorry, Professor Brum, I know it's very simple, but for the talk it helps, okay? So we can think about heart failure induces multiple triggers that cause ultimately muscle weakness, okay? And one of these, we get an increase in protein degradation, and that leads to muscle wasting or muscle atrophy. And if we look at a couple of other mechanisms, we get an increase in reactive oxygen species, and these can impair some contractile proteins, and we get contractile dysfunction, okay? So this is important to realize at this point that we can get a loss of muscle strength without losing muscle mass, okay? The muscles themselves just become weaker. So if we normalize force to muscle mass, we still get a reduction in heart failure patients. And mitochondrial dysfunction, we all know the importance of that in bioenergetics, oxidative metabolism. That plays a key role in inducing some of the greater fatigue we see in the patients. But ultimately, what we have then are this contractile dysfunction, this loss of muscle mass, and that drives an overall muscle weakness in the diaphragm as well as the limb muscles, okay? Limiting or reducing, causing greater symptoms, reducing quality of life, and ultimately it can contribute to an early mortality. So, today, we're going to go a bit deeper into some of those mechanisms. And we're going to start by looking, okay, this is typically heart failure. We have two types, okay? Heart failure with a reduced ejection fraction. This is the classic heart failure. Systolic impairments. And this heart failure with a preserved ejection fraction, okay? Today we're going to focus mainly on heart failure with reduced ejection fraction, HFrEF, and I think Professor Brum has focused more on HFrEF in some of her papers. And what we can see here is what drives the development of heart failure are many risk factors. So we have cigarette smoking, myocardial infarction, a heart attack, diabetes, obesity, hypertension, many risk factors. As I look around the room, I think all of you don't have many of those risk factors, so that's good. Okay, I think chance of heart failure are low, great. If we look at the risk factors per se, we can see these are ranked in order of severity. MI or heart attack seems to be number one. So we're going to go through some of these, and the key question, what we asked in some of the next studies I'm going to present is, before heart failure actually develops, okay, do these risk factors, can they actually induce respiratory or limb muscle weakness, okay? So even before heart failure fully develops, if people are simply smoking or have diabetes, can they induce a lot of the muscle dysfunction we see in heart failure? So the first one is hypertension. So what we used here was an animal model. So essentially we gave a high salt diet to mice, and we took the kidney out, a nephrectomy. We implanted a DOCA pellet, which essentially is a precursor of aldosterone, okay? So they're disrupting the renin-angiotensin system. We can see we got this systolic increase in blood pressures. And we also trained some of the mice for 2 weeks performing high-intensity interval treadmill exercise, okay? And what we did, we isolated some diaphragm strips, muscle fibers, and also some limb muscle, and what we can see is in those mice with hypertension, okay, so this is after 4 weeks, we get around a 20% reduction in diaphragm forces. This was essentially completely preventing those performing the high intensity interval training, okay, and this is in the diaphragm muscle. When we did moderate intensity exercise, we actually didn't see any benefits, suggesting, at least in hypertension, we need to do high intensity training to induce the diaphragm benefits. And we didn't see really much changes to the limb muscles. Some of the mechanisms, well, NADPH oxidase, we found an increase in hypertension, but this was reduced after exercise training. So Professor Brum has shown the key role of NADPH oxidase in driving muscle wasting and weakness. And if you look at some redox readouts as well, so superoxide dismutase, a key antioxidative enzyme, levels down in hypertension, but exercise training increased. Okay? So it seems to be key role of reactive oxygen species, okay, an increase in ROS, driving some of this diaphragm weakness. And when we looked at kind of alterations, oxidative modifications to some of the key contractile proteins, we saw myosin heavy chain, protein oxidation of that increased, but prevented or attenuated with exercise training. So clearly suggesting ROS are playing a key role reducing these forces. To provide a bit more evidence, we also incubated some diaphragm fibers with hydrogen peroxide, okay, a reactive oxygen species, and what we can see is after incubation, we just did 30 minutes, okay, we got this reduction again in diaphragm forces of around 25%, but in mice that had pre-trained for 2 weeks. Okay, so we're increasing their antioxidative defenses. We essentially prevented that. Okay, so that's the first risk factor. So hypertension does seem to be playing a key role in driving muscle weakness. If we look at cigarette smoking, in this study, this was actually done up in Norway with Professor Ulrich Wisloff in his lab. And what we can see here is we did 20 weeks of cigarette smoking, and they performed afterwards in mice 6 weeks of high-intensity interval training. They didn't develop any alterations in the pulmonary system, okay, so a preclinical model of chronic disease, say lung disease or cardiac disease. We saw more moderate dysfunction in the diaphragm, but again, prevented by high-intensity interval training. The limbs, we didn't really see an effect again. But we looked at the ROS measurements, and again, markers of ROS NADPH oxidase up in the smokers, and this was largely prevented in those that had performed high-intensity interval training. So exercise seems to be very good at protecting muscle function from its antioxidative benefits. So, moving on again now to myocardial infarction. So we looked at what's the effect of an acute myocardial infarction, essentially a heart attack. And in a mouse model again, we induced an MI and looked at muscle function 72 hours later, okay? So typically if you have a heart attack, we wouldn't think 3 days later that's really going to impact your diaphragm or limb muscles. Okay, well let's see what happened. So you can see here, this is the left ventricle, so just after 72 hours you get this really nice thinning of the left ventricle wall. And the echocardiography, you can see this dilated left ventricular chamber. And, this also surprised us. What we saw again in the diaphragm was this reduction in forces by around 20-25%. Okay? This is just after 72 hours. So what we kind of concluded from this was actually a lot of patients who have a heart attack, they may develop inspiratory muscle weakness, respiratory muscle weakness really fast, and that can contribute to a lot of symptoms. And a lot of us didn't really think that was occurring. We went after some ROS measurements, so we used, looked at post-translational oxidative modifications, carbonylation in particular, and what we saw is sarcomeric actin that was severely carbonylated, and creatine kinase, okay? Key proteins involved in skeletal muscle contraction. So, if you look carefully here, we now have moved on 10 weeks post-MI. Okay, so typically this is now an overt model of heart failure. So these mice, you can see the left ventricle is a lot thinner than before. Okay, this is 10 weeks post-MI. Full heart failure is developed, and we did the same measurements, but essentially we add an extra group, and they performed 9 weeks, and we did moderate intensity training. Okay, high intensity, when you have an infarct, is pretty tricky. And again, what we saw, okay, with heart failure, we got this reduction in contractile function, but largely prevented in the trained animals. Looking at the markers again, we can see trainings reduce a lot of the carbonated proteins. Great. And at this point, what we also could see is some markers of protein degradation were elevated. We didn't see this 3 days post-MI. In particular, the E3 ligase, that for many conditions is necessary for muscle wasting, that was upregulated following heart failure, as well as proteasome activity. The main pathway of protein degradation reduced with exercise training. Okay, so some key points so far. Heart failure induces muscle weakness. Okay, I've shown you some patient data, some animal data. That was in both types. But this seems to be early onset by a number of key risk factors, okay? So many people, even before heart failure is onset, or they develop it, they probably have muscle weakness in the diaphragm, particularly the diaphragm, at least from these data. The limb muscles, it seems to be later the limb muscle dysfunction develops, and that's probably an overt heart failure. As I said, yeah, the diaphragm seems to be more sensitive. We're not sure why exactly that is. And at least one key mechanism seems to be this change or this increase in oxidative stress. And exercise training seems to be really, really good at preventing this shift towards a pro-oxidative state. Okay, so last slide we finished on this discussion of markers of protein degradation seem to be up. In particular, this E3 ligase muscle ring finger 1, MRF1. Some of you have probably heard of that. And if we look a bit closer at this, we can see if we're going to increase muscle wasting, typically what happens, we upregulate E3 ligases, okay? And these E3 ligases, you can zoom in here, they essentially tag proteins with ubiquitin. Once proteins are tagged many times with ubiquitin, they're recognized by the 26S proteasome. You can think of that as a rubbish bin, okay? So once proteins are tagged by ubiquitin, then this rubbish bin actually opens the door and it degrades them. And that really contributes to muscle wasting. And one of these key E3 ligases are MRF1, okay, muscle ring finger 1. We can see the catalytic domain, here's this ring finger that really binds ubiquitin onto the proteins. And we have this central region here that actually just binds to the proteins themselves, okay? So all of this, so far, a lot of it has been animal stuff. And many of you are thinking, okay, great, nice. Does it translate to patients? That's what really matters, okay? So we got some patient biopsies here. These are from the clinic at Leeds, and we can see typically we do see a fiber atrophy, around 20%, particularly in type 2 muscle fibers, okay? Type 1 seem to be protective. And what we see when we look at mRNA levels of MRF1, we see this upregulation in CHF patients. So it seems to confirm some of the animal findings. These are data published from the Leipzig lab, where I used to work with Professor Volker Adams, and we can see in patients, those that perform exercise training, similar to the animal models I presented, their levels of MRF1 are normalized. And that's highly correlated to maintaining muscle mass. The question is, okay, nice associations, but is this causal? Or is MRF1 necessary for fiber atrophy and heart failure? So in this study, what we did, we induced heart failure by actually injecting monocrotaline, and that essentially induces pulmonary hypertension and provides a form of right ventricular heart failure. Okay, so it's a nice model to investigate. So you can see what we also got was MRF1 genetic knockouts of MRF1. Okay, so we genetically deleted the MRF1 gene, and we then asked the question, okay, do these also suffer muscle wasting? So both sets, the wild types as well as the MRF1 knockouts, they develop similar levels of right ventricular remodeling and heart failure. But what we can see here, if we look at one muscle, the cross-sectional area of the tibialis anterior, leg muscle, we can see this huge wasting in the wild types, completely prevented in the MRF1 knockout animals. Looking at wet weights, some more leg muscles, EDL, soleus, tibialis anterior, we see around a 10 to 15% wasting in just wet weights in the wild types. In the knockouts, this is pretty much largely prevented. Quite scary when you run a study and you start to see these findings. And when we looked at function, okay, does this translate to function? We can see again 20% reduction in function of isolated soleus muscle, and that was prevented in the knockouts. You can see MRF1 clearly upregulated, and I'm going to introduce something a bit more complicated. So MRF1 actually comes from a family of 3 MRFs. So we have MRF1, MRF2, and MRF3. And previously, we thought just MRF1 is the main protein involved in muscle wasting. But we collected some data previously that says, well, maybe, MRF2 is also playing a role. And when we looked at levels of MRF2 in the muscle, what we found that was also upregulated. So we said, okay, well, let's generate some MRF2 knockout mice and see what happens. And we were pleasantly surprised, because if we look at fiber cross-section area in the MRF2 knockouts, also we don't see a wasting. If we look at the wet weights, once again, MRF2 knockouts here don't really show any of the wasting. And when we looked at function, identical to the MRF1 knockouts. So these data suggest MRF1 and MRF2 seem to independently drive muscle wasting. But we know from previous publications MRF1 and MRF2 may interact. Okay? And essentially from the data, what we find, it seems to be MRF1 is the key driver, and that may interact with MRF2. Okay? I can't go into too much details on that point, but we essentially went from the point, okay, we knocked the gene out, great, but in patients, how easy is that to do? So when we get the patients that come to the clinic with heart failure, it's not so easy. We can just say, okay, let's delete the MRF1 gene. Okay, it doesn't happen like that. So what we really need is to translate this to more in vivo treatments, particularly drug treatments. So what we focused on the last few years has been developing small molecule inhibitors. And in this, we used alpha technology and screened over 130,000 compounds. And what we assessed was, okay, what compounds could actually inhibit the interaction of MRF1 central, so the MRF1 central part of the protein, to it binding to titin. So a lot of you are probably familiar, titin is the biggest protein in the body, very important for structure in the muscle cell. So we assessed, okay, from all of these 130 compounds, which one could inhibit this interaction between the two proteins? Long story short, we got down to this one. Okay, this one compound, MBL ID number 704946. When we did some initial analyses, so in vitro, what we saw, at least MRF1 mRNA, when we treated them with dexamethasone, okay, that's a glucocorticoid, induces wasting. And we can see treatment just with dexamethasone alone induced myotube atrophy, or upregulation in MRF1 mRNA, blunted with the new inhibitor. Looking at myotube size again, we saw this wasting with dexamethasone treatment and blunted when we incubated with our novel small compound 704946. Great. So far, so good. We were very happy and we went for a nice German beer after this. And then, when we were sitting in the pub, we were like, okay, this is good. In vivo. Can we translate this in vivo? So a few beers later, we all agreed we would try. And we did. So we used the same model with the monocrotaline treatment with right ventricular heart failure. And in this mouse model, when we mixed this compound in with the chow, so very easy, what we saw was tibialis anterior fiber cross-sectional area. We saw this wasting in heart failure mice, largely prevented when they were fed the compound. Okay, this was 6 weeks of treatment with the compound. Again, looking at some function in the diaphragm, looking at power at this point, we measure shortening velocity as well. And we can see in the heart failure, this kind of downward shift in the power curve, largely prevented with the compound. So this is important because it suggests the compound not only benefits fiber size, but also contractile function as well. As expected, so MRF1, levels of MRF1 were downregulated. Complicating the story a bit, MRF2 was also downregulated, so we think the compound may actually be also targeting MRF2. We have some data saying it's specific for MRF1, but we're not sure if MRF1 is interacting with MRF2 or the compound is directly inhibiting MRF2. We're still trying to work that out. But, looking at some other measures of protein degradation, ubiquitination of proteins of actin was downregulated following compound treatment, as well as proteasome activity. We then did some proteomics, okay, so we wanted to have a bit more of a global assessment. So we ran some proteomics on the muscle samples. And what I really want to highlight, we essentially found 5 proteins that were highly significantly and differentially regulated between those that were treated with and without the compound. And what that told us was, okay, this inhibitor is not only impacting protein degradation pathway, or at least the ubiquitin proteasome system, it seems to be impacting protein synthesis, so translation initiation factors are being impacted, key for protein synthesis. Apoptosis, another pathway for muscle wasting, that was also downregulated with the compound. And here we can also see some mitochondrial proteins that were downregulated, the compound prevented that. This was interesting because for the first time we started to see, well, maybe MRF1 not only impacts wasting, but it could be targeting the mitochondria, and that's going to have important consequences. And in a recent study, this has just been published, so we now use the myocardial infarction model. We treated those also with the compound. We saw some, slight effects on muscle wasting, not as big as before. Some effects on contractile function, but the real impressive and surprising effects are actually on mitochondrial measures. Okay, so we essentially were able to normalize protein expression of mitochondrial ribosomal proteins and complex 1 activity. And when we went back to look at the knockouts, we can see citrate synthase activity in heart failure is reduced by around 40%. Okay, so citrate synthase, a key marker of mitochondrial content. And in the knockouts, that was largely prevented. So these are really strong data suggesting for the first time that MRF1, which we thought was only involved really in the muscle wasting protein degradation pathway, is actually impacting the mitochondria. Important for metabolism and mitochondrial signaling. So, another wrap up, heart failure, okay, it seems to reduce muscle wasting, and MRF1 and MRF2 seem to be key, causal for this, but we can actually inhibit MRF1 with this new compound we developed, and that seems really effective for treating both wasting and contractile dysfunction. And what we've recently found is MRF1, inhibiting MRF1 actually seems to allow mitochondrial function to be normalized. Okay? So just moving on to the very last part of the talk. I think I've got time. I'll just 12:30. Okay. So what we essentially have got to at the current point, and that's really what the lab is currently working on, is this triangle between MRF1 signaling, mitochondria signaling, and fiber atrophy. Is there a key mechanistic link between this triangle? That should be number 2. I can count when I did this. And do these animal findings translate to humans? Okay, that's the real tricky question, the most important but very, very tricky to feed humans this compound we've recently developed. So that may take quite a few years. So, at least to provide some initial evidence, what we've been doing over the last 12 months is collecting human biopsies, and this is from the pectoralis major muscle, so a skeletal muscle here. So when a lot of patients go in for pacemaker surgery, I have a very nice clinician, and he's providing me with some tissue from the pec muscle. Okay, and that's really allowed us to start to investigate some of the links between this triangle. And you can see we've got good numbers, around 44 controls and around 58 heart failure patients. So we've used the ROS machine. I think you've just got one in Professor Brum's lab. And what we can see really across a lot of the complexes, so these are impermeabilized muscle fibers. Given certain substrates and inhibitors, we can see particularly complex 1 and complex 2, we see around a 20% reduction in mitochondrial respiration. Okay? So this is in situ measures, much better than some of the in vitro measures we have available. When we look at the fiber wasting, I showed some of this, we see the fiber wasting, we see the mitochondrial dysfunction, and we see activation of MRF1. So that does support some link between this triangle. What's actually, we just found a few months ago, this complicates the situation a bit more. So those of you who are interested in sex-specific effects, mostly research is very biased towards recruiting male participants. And we were lucky enough to have enough females to separate out the female patients and the male patients and to see if they responded the same, in terms of mitochondrial function at least. We're currently working up the muscle wasting angle. And if we look at just exercise tolerance, we know females have a lower exercise tolerance than males. We don't really know why. And in this study, what we actually looked at, we compared them to their healthy counterparts as well. And what we can see in the males and the females, mitochondrial respiration is reduced. This is complex 1. Okay? So nice and easy. Nothing surprising. But when we actually looked at measures of mitochondrial content, we saw a much greater reduction in the females, and we didn't see that in the males. So when we actually normalize the mitochondrial function to intrinsic mitochondrial respiration, what we see is females have normal intrinsic mitochondrial function or respiration, but the males seem to have intrinsic impairments. Okay? So really what these data seem to suggest, in females, heart failure patients, they have problems with the quantity, the amount of mitochondria, but in males, they actually have enough mitochondria, but they're just not working correctly. We looked at some markers of fission and fusion, just to get an idea if anything differs, and in gene expression at least, mitochondrial antioxidant, SOD2, reduced only in females, OPA1 important for mitochondrial quality control, more downregulated in females, and the master regulator of mitochondrial biogenesis, PGC1 alpha, particularly impacted in females, in both gene and protein levels, and not so much in males. So we think we do have some underlying mechanism there. We're currently, that study's ongoing. So the last bit of novel data to show is going back to this triangle, MRF1 atrophy and mitochondrial dysfunction. Bringing in the diabetes angle, okay, this complicates the situation a bit more, but it helps us get to the end of the story. Patients with heart failure and type 2 diabetes, huge problem, particularly in Europe. They're increasing in prevalence. Prognostically, they're 30% more likely to die than patients without diabetes. And we can't really deal with these patients. We don't know how to treat them. Okay? So what we've recently got into is looking at these patients, looking at the skeletal muscle. Are they responding the same as heart failure patients without type 2 diabetes? So, using the same muscle samples, the pectoralis major, during routine pacemaker surgery. So what we can see here is this much lower exercise intolerance in the diabetic heart failure patients. They have much severe symptoms. But looking at measured cardiac function, they're matched. Okay? So again, those of you, next time you talk to your cardiologist, tell them, okay, it's not just the heart, something peripheral is also going on, that's a problem. So, if we zoom in here, so you can see we've got pretty good numbers, controls, type 2 diabetic patients, heart failure patients, and diabetic heart failure patients. And looking at in situ mitochondrial respiration, we can see this is complex 1, oxidative phosphorylation. In particular, we see this downregulation in the diabetic as well as heart failure patients, okay? But when we look in combination, we see a severe mitochondrial pathology, okay? So this is the first time we've really found this in these patients. They have a huge increase in mitochondrial ROS production as well, measured by Amplex red. And we start to see markers, gene expression of, complex 1 subunits, superoxide dismutase 2, severely downregulated in the patients with diabetes and heart failure. Looking at fiber atrophy, wasting, again, severe muscle pathology. All of the fibers, muscle fibers in diabetic heart failures, severely downregulated, okay? MRF1, greatest activation in the diabetic heart failure patients. When we plot these data, we can see this really strong correlation between the level of MRF1 and the fiber cross-sectional area. When we plot again mitochondrial complex 1 respiration, that's very strongly correlated to fiber cross-sectional area. So supporting that link between here. MRF1 potentially inducing mitochondrial dysfunction to enhance ROS, which may drive greater MRF1 and ultimately increase muscle wasting. So it's still a proposed hypothesis, work is ongoing, and we're not really sure what's causing what, but we think MRF1 may actually be inducing some of the mitochondrial dysfunction to cause greater muscle wasting. Okay, so this is summary slide, pretty much. Today we discussed heart failure, we have muscle weakness. Some of this is caused by muscle atrophy, in particular due to MRF1. We also can see loss of force independent of muscle mass. Contractile dysfunction seems to be driven a lot by increase in oxidative stress. Both of these contribute to muscle weakness in the diaphragm and the limbs. Exercise training seems to target a lot of mechanisms. Okay, so oxidative stress, mitochondrial dysfunction, as well as the protein degradation. When people are too sick to do exercise, or when exercise simply doesn't work, what we've developed are some novel small compounds that seem to directly inhibit the MRF1 protein to prevent muscle wasting. And to complicate things further, we're now seeing sex-specific effects in the mitochondrial dysfunction, and we're looking at that in terms of muscle wasting. Okay, so that's pretty much it. I'm going to fast forward these final slides. I haven't got time to show you all of this, and I think you've got plenty of other things to get on with today. Okay, so that's pretty much what I just concluded. So, thanks very much. If you have any questions, fire away. Otherwise, thank you for your time.
Tá funcionando. Agora sim. Está aberto para perguntas. Vocês têm perguntas? Alguém quer fazer alguma pergunta? Senão eu posso começar. I can start. I have a question for you. I don't know if I missed this data, but have you checked the mitochondrial respiration and nerve knockout? In nerve knockout mind.
So
Just to see if it would affect
when we did the study,
in heart.
we didn't have the equipment available to measure the mitochondrial respiration. So all we have from the MERV1 knockouts are the measures of, say, citrate synthase activity, which
It was reduced.
so it was reduced in wild type, but in the knockouts we didn't see that reduction.
And another question, you showed separately the MERV1 knockout mice. Have you checked the MERV2, how was expressed and function? Because if you have the MERV1 knockout, it's entire body knockout, right? It's not specific
No,
to the
it's
muscle.
global knockout.
It's global knockout. So if you delete the MERV1, what happens with the MERV2?
Yeah, so
And
I
vice versa.
skipped through some of those data quickly because they take a bit of explaining. So from these data, it seems in the MERV1 knockout, MERV2 is affected. MERV2 levels are down. Then the MERV2 knockout, we don't really see the effect on the MERV1. So I think that would suggest the MERV1 is the key regulator. Yeah, that's a good question. But we're still trying to figure that out.
Alguém da audiência? Alguma questão da audiência? Marcelo, junto. I have more questions if you don't. I do have one more. In the patient studies, have you tried or think or thought about doing inspiratory exercise training in these patients and see if the function, how much does that is comparable to exercising the whole other muscles?
So
with
I would love to do it, but the clinicians don't want to do it. So
they don't want, because it's a physiotherapy for the respiration. When you do like this, I don't know if you.
So at least from my perspective, the clinicians are really happy to contribute to studies. But once it comes with doing any interventions, such as exercise training, they don't want to do any of that. So it limits the research that I can do. But I think in the past people have done it, particularly in Brazil, you've done a lot. There's a lot of the groups here have done this.
Because it works in heart failure patients, but we don't study the diaphragm. So it would be interesting if you for you to see, because you particularly study this muscle, right?
I guess the question is also the aerobic treadmill running. What is the systemic benefit versus local? Because we're still not too sure. I think in heart failure, the systemic benefits versus the local benefits.
The sex difference the sex difference that you found were only in the human study, right?
Yeah.
You didn't try mice yet.
Not yet. Not yet, but I think I may have data from all of the animal studies where I can separate out to start, even the MIRF1 knocks. I think we've got some female and male mice where I can start to see if there's differences there as well. It's tricky to get that underlying mechanism actually.
It's totally worth looking at.
Yeah, definitely.
Okay. I have another question for you, is that in the cachectic stimuli, you see much more muscle wasting in type 2A, type 2X fibers, but not in type 1. And do you have an explanation for that, or can you think about mechanisms? Why oxidative fibers are more resistant to
Probably mitochondria. They have higher mitochondrial content, which is playing a role.
Then I was puzzled by a data that you showed us. You say that type 1 fibers are more resistant to muscle wasting.
Yeah.
However, the diaphragm wasting anticipates the skeletal, the other skeletal muscles, the lean skeletal muscles. And as far as I know, the diaphragm is mostly oxidative fibers, right?
So, first point, go in the type 1. I think that's because we have higher levels of also PGC1 alpha, which blocks FOXO going into the nucleus, upregulating the atropines. So I think that's probably why we don't see the effects in the type 1 fibers so much. Diaphragm is really interesting in terms of fiber type. It's around 60% type 2, 40% type 1, or 50-50.
Even in humans?
Yeah, it's around 50-50, but
it's 2A then.
It's the thing though, that the typical 2A are highly oxidated in the sense that the type 2A are more oxidated than your typical type 1s. So it is surprising, you know, particularly if it becomes trained. So a lot of the patients are breathless and they start to actually train the diaphragm. Yet we still see a lot of the dysfunction. So at the minute we don't know exactly why. So it could be metabolic properties. I suspect it's something to do with proximity to the heart. So in terms of signaling, paracrine or whatnot, maybe at closer proximity, blood flow is much higher. So if it's subjected to more of this systemic inflammation because of the higher blood flows, that may be causing some of that.
That's a good answer for that, because but
it's very sensitive. It seems to be really
it's
sensitive.
more sensitive than the oxidative fibers that are far from the heart, right? And do you think the phrenic nerve or it's also altered the neurotransmission?
So at least rat data, if you stimulate it directly, you know, just the muscle, you see I think around 20%. If you stimulate it via the nerve, you see an even greater reduction in forces. So it definitely does seem to be some phrenic nerve impairments as well.
Mais alguma questão? Aqui. E de lá. Se apresenta para ele.
Thank you for nice results. I'm Professor Edila Mar, from here, Physical Education School. I'm a biochemistry professor. And you showed the first slides, the ovarian cancer. And you showed that...
ovarian cancer.
Yeah. Yes. Why some patients do not lost skeletal muscle mass, and the others
I'm not sure.
lost?
So that study, we didn't perform the study. It was someone else's data. but they essentially saw a split in the data. So, you know, it could have been related to maybe some severity of the data, but I'm trying to think that I think the patients were quite well matched between, but I can't remember the exact study.
Okay.
So maybe any students, if you want the exact answer, go on the paper. It was in JCSM.
Okay. But you didn't
No,
experiments
no.
to check the skeletal
No.
muscle, the fibers, or
No.
no? Okay.
It's complicated, I think, because particularly with patients, because there's so many things that are going on in terms of, you know, the baseline physical activity, the medications they're on, their diet, genetics and whatnot, and also a lot of them lie. So when they say they're doing exercise, they're not really doing anything. So it's always tricky to say why are some suffering more than others. I'm not too sure.
Okay, I think we are ready to finish, and I would like to thank you for your talk, and thank you the audience for coming here and to appreciate your data. And now I'm going to switch very briefly to Portuguese. Muito obrigada, pessoal, pela presença. E então vocês deixem o resumo dessa palestra nos caminhos do professor Rômulo. Muito obrigada por ter a companhia de vocês esse semestre. Muito obrigada a todos que vieram assistir. E nos vemos no próximo semestre. Obrigada. And I would like to give you just this from physical education in this sports school. Thank you. Thank you, Scott.